Welcome everybody, thank you for coming. We'll get right to the business. I wanted to welcome Taury Smith, Langhorne's son, who's been around a long time. Give a little bit about his background. He earned his BS in geology from Temple University, his PhD from Virginia Tech. And then he went on to work at Chevron for a short time, and then the University of Miami, where he was a research scientist. And then he went on to become a state geologist at New York State, where he worked for 13 years, and now works as a consultant. He became interested in geology in Islesboro during the pandemic after the Historical Society asked him to do a lecture on geology of the island. And I want to welcome our rock star for tonight.
So Patrick asked me back in 2019, I guess, if I would do a talk on the geology of Islesboro, which I'd come here my whole life. I've been a geologist for 30 years, and it's not the kind of rocks I study normally. These are called metamorphic rocks, and I just thought, oh well, they're cool looking, but I never really thought about them that much. And then I said, well, yeah, I'll do the talk. And then I got out and had a look. I thought, well, I'll just pull the geologic map out, and I'll take a few pictures, and I'll make a nice little talk. And then I took the map out, and I was like, this is not what the map said, you know. And I went around, and I realized the map had a lot of problems. The original bedrock map that we had. And so I did the talk for the IHS, but then I got really interested, and I started walking it out, and I Googled geology of Islesboro, and I found out that there was active geological research going on here, and that there are all these cool geologic stories here. And I connected with these other geologists, Justin Strauss from Dartmouth College and Doug Royce from the University of Maine, and then Justin had a grad student here last fall. Justin took his sabbatical here on Islesboro and worked on making a new bedrock geologic map of Islesboro. And there they are. I don't know if any of you met Justin last fall, or Luis, who did his master's out here, and then Doug Royce, who's been around even more frequently. And here's and yours truly. That's the team there. And so yeah, we got interested, and I started like spending half my vacation walking out the coastlines of Islesboro and the surrounding islands, and it seemed like every time I thought I understood it, I'd go around the corner and there would be some unexpected thing there. And I like to call it the geological gift that keeps on giving, because it's just so fascinating. There's every kind of rock here. It's just fabulous. So I made a map that I thought was a good improvement on what the existing one, and then they took what I did and built on that, and then last fall they went crazy and really did a fantastic, very professional job. And then they produced this map, which I didn't have anything to do with this final version, but they built on some of the work that I did. And so I'll go through that. What I'm going to start out with is a little background geology, just so you get a sense of what I'm talking about, you know, a little bit. You probably all have heard that there are three main kinds of rocks. There are igneous, metamorphic, and sedimentary rocks. And igneous rocks form from molten lava, from magma. They burn and then they cool and they become a rock. And that would be something like basalt or granite. Sedimentary rocks would be like sandstone, limestone, shale, rocks like that, dolomite, and we have a lot of these here on the island. And then both the igneous and the sedimentary rocks have been metamorphosed, so we have rocks that are called things like quartzite, marble, phyllite, schist, and amphibolite. You're all going to be experts on all of these by the end of this talk. But the neat thing is we have it all here. It really is just an open laboratory on geology. Now we're going to zoom out to the big picture, because this plays an important role in the of Islesboro is all these rocks formed somewhere else. They didn't form when Islesboro was part of North America. It looks like they formed when Islesboro was, the rocks that make up Islesboro were situated on the west coast of South America. And I'll show you how we've worked all that out. But we've been on quite a journey that's passed through the South Pole and ended up eventually here. So the Earth is composed of 15 or 20 tectonic plates. And these plates are all moving relative to each other. They're in constant motion, although they move so slowly that you would never notice it. But this is the great unifying theory of geology, is plate tectonics. It explained all these things which we had only poor explanations for before. Now with GPS technology, they can actually work out the exact rates that the plates are moving toward or away from each other. And for instance, the Atlantic, this is in centimeters per year, the Atlantic is getting about 2.3 or 2.5 centimeters wider every year. The European plate is moving away from the North American plate. That's about an inch per year. But if you have tens of millions of years, you can go a long way, even at a very low rate like that. So I'm going to now jump out of this and show you all an animation of plate tectonics. So this was made by a guy I know called Chris Scotes, and the legend should pop up here right about now. Come on. Oh no. Okay, I have to close it up again. Had it all queued up for you.
We have a song and dance to fill in.
What?
Nothing.
There it is. There it is. Okay. Now, so there's the legend. So dark blue is deep ocean, light blue is shallow ocean, tan is lowlands, and like reddish is our mountains. So we're going back through time here. This is 10 million years ago, 20 million years ago, and that's the time period down on the bottom right. And so we're going back through time, and you see Pangea is starting to assemble itself as we go backward through time. See that? So back in the Jurassic, 180, 200 million years ago, you could have walked across all the continents. They were all connected. They were all one supercontinent, we call it, Pangea. And we were connected to Africa and South America like that. And then we'll go back through time, and then this is the time before Pangea. And Islesboro is actually part of this little chain of islands right here. Do you see the arrow? Yeah. And so if we go back even farther, it's at the very South Pole there. See that? And it's wedged between the Baltics, like around the Caspian Sea or the Black Sea area, and the west coast of South America. And so here it is, still part of the west coast of South America, because if you follow this landmass here through the animation, you'll see it becomes the west coast of South America as it rotates around. See that? Yeah. Yeah. So it's formed like in next to Colombia, basically. So, so there are people that dedicate their whole career to working out where the plates have been through time. And there are all these different lines of evidence that they use. They use magnetics, and as long as there were fossils, they use fossils, and they can work that out. But of course, the older it gets, the less, the less certainty there is going back through time. So keep all that in mind, and because that animation only goes back 750 million years. But some of these rocks formed before that time, so we're going to have to use other methods to work that out. Now, this idea of plate tectonics was first proposed by this guy named Alfred Wegener. It's one of the more interesting stories in the history of geology. He was a German scientist who became convinced. Actually, they saw that South America and Africa fit together like puzzle pieces. The day they made the first map, they were like, oh wow, those look like they fit together, you know. But and he proposed this idea of Pangea, that once all the continents had been together, and he used a lot of different lines of evidence, and he died with only his students believing him. Everybody thought he was a lunatic, because of course the continents don't move. And he called it continental drift. His main problem was that he didn't have a mechanism by which to explain why the continents would move. He thought the tides were moving them, which was wrong. He was wrong about that. So it wasn't until this guy, Harry Hess, he was a professor at Princeton, but prior to that he was charged by the Army during the war with mapping the seafloor of the Atlantic. And he found that in the middle of the Atlantic there was a ridge. There was a chain, a high ridge that runs down the middle of the Atlantic. And later on, when he became a professor at Princeton, he came up with this idea that they call it a spreading ridge, that hot lava was coming up with this ridge, and then the plates were moving apart from each other there. And that was the missing piece that Wegener didn't have. And within a few years, and this is in the 60s, so not that long ago, geology was totally revolutionized by this idea. And I went to school in the 90s, and I still had a professor who was trying to prove that it wasn't happening. Yeah. So it's that recent that this was a controversial idea. But the beauty of it, so what he showed, what we now know, these are the spreading ridges. And you see they're running everywhere. And they're in the Pacific as well as the Atlantic. So the plates move away from each other there, and then where they collide with each other, well, here it is. So the hot molten material comes up at the ridge, the plate pushes the plates apart, and when they collide with another plate, one goes under. It's called subduction. It gets subducted under that, and you see a mountain chain forms there. Because the one is being pushed under the other, and it's crumpling that up and lifting it up and raising it and turning it into a mountain. Volcanoes also form there. So when continents rift apart, Pangea was all together, and then it came apart again. And that's a process called rifting, which turns out to play an important role in the geology of Islesboro. So heat builds up under the supercontinent, and eventually it starts to pull apart, and a rift forms, a rift valley, where a lake might form, and you see there's a lot of volcanoes and stuff there. And I think a lot of our rocks formed in a setting like this, the rift valley. Eventually a sea forms, and eventually an ocean between the plates. And that's called a divergent plate boundary, or a rift. And then where the plates collide with each other, it's called a compressional, or a convergent boundary, and that's where all the volcanoes in the world are at convergent boundaries. All these yellow things are volcanoes, and they're all where plates collide with each other, where they're moving toward each other. And one's getting pushed under the other, and molten lava comes up through the volcanoes. So plate tectonics explained faults and earthquakes, it explained mountain ranges and why we have them, it explained volcanoes and why they occur where they do. So it really was the great unifying theory of all geology. So at convergent boundaries, you can get oceanic crust colliding with continental, oceanic colliding with oceanic, or continental crust colliding with continental crust. And this one is important for our story because it explains all the metamorphism that's gone on in the rocks of Islesboro. It was when the little sliver of islands collided with North America, got deeply buried, and that's when all the metamorphism occurred at a plate-to-plate convergent boundary. So, when metamorphism happens, rocks are altered by increased heat and temperature. The deeper in the earth you go, the hotter it gets, and the more intense the pressure. And rocks change, the minerals, new minerals form, and rocks really look different. So this image is meant to show a rock that starts out as a shale, which is sort of a fissile, flaky rock. You bury it a little bit, it becomes slate. Bury it a little bit more, it becomes a rock called phyllite, which we have a lot of here on the island. Bury it a little more, it becomes schist, which is mica. Like, if you've ever been in Central Park, that's beautiful mica schist. And we have that here on Islesboro, on 700 acre spruce and out on Hutchins Island. We have nice schists here. So that indicates pretty intense metamorphism if you get schist, a little less so if it's phyllite. And then finally, when sedimentary rocks are deposited, they're almost always deposited in nearly flat horizontal layers. So when they first start out, they're in flat horizontal layers, but almost all the rocks on Islesboro are vertical. And what's happened there is due to the compression and the collision, these once horizontal layers fold up like an accordion. See that? And you see it if you go out on Turtle Head, you'll see the rocks are folded like that. And that's an indication that we were at a convergent plate boundary, that two continents collided with each other. And there they are. I didn't even need to have you imagine Turtle Head. There it is, with beautiful folds. And lots of the layers are vertical. See how the layering in that is vertically oriented rather than horizontally? Well, when it started out, it was horizontal, and it was due to this folding that the beds are now vertical. And then finally, one more piece of the puzzle is anytime you get folding in a convergent plate boundary like that, you also get a lot of faulting. Reverse faults where the hanging wall goes up over the foot wall, and that's exactly what's happening here. This has moved up, and this has moved down in a relative sense. And we also have a lot of what are called strike slip faults that cut across the island. On this map that I've handed out to you, those are all the black lines that you can't see in the dark, but that cut across the island that have little arrows with relative motion on them. And I'll explain that more as we go along. So, that was the Geology 101. You got it all? You ready for the test now? Okay. Finally, one thing that geologists make, and one tool that we use are these bedrock geologic maps. Bedrock is the solid rock that's under everything on Earth. Like, we go outside, we'll see some soil, but if we drill down far enough, we would eventually hit solid rock. That would be the bedrock. And which, fortunate for us, geologists here on Islesboro, we have a lot of bedrock exposed all around the coastlines, so it makes mapping easy. A lot of times when you have to map the middle of the United States, you count on a road cut or a quarry or something like that, or core drilling or whatever, because you don't get a lot of natural outcrop. Here, 70% of the coastline or so is natural outcrop, so it makes it a lot more fun and a lot easier. But the whole country has been mapped, the bedrock's been mapped, the states have been mapped, and then they map something called quadrangles, which are smaller maps that they do in greater detail. And this is the map that I took out when I started here in 2020, that I thought, geez, this map's got a lot of problems, you know. But you see, he mapped a pretty big area. All those colors represent different age, mainly granite up here. And that was this guy's bag, was granite. He was into granite. That was his thing. So, Islesboro was this oddball thing that had all these metamorphic sedimentary rocks on it. I just don't think he was all that interested in what we had here. Although he did do some interesting age dating and so forth. And I shouldn't trash him. I mean, it was really hard. You really needed, we had a team of 4 people working intensively for a couple of years to get it close to right, you know, so it was very complex. So there's the map that he made, and then that's the map that I made, which I like my colors. You see, it's quite different from what he had. And there's a lot more colors, a lot more detail, and then I'm not going to get into every detail that I changed, but a lot of the ideas a lot of the things I recognized ended up in the new map, which is this. But they did a fabulous job. That Justin Strauss, the guy from Dartmouth, he's the best geologist I've ever worked with. He knows. I'm good at sedimentary rocks. That's my thing. He knows igneous, metamorphic, all these age dating techniques and stuff. I mean, stuff I've never heard of. So we got the best. We got the very best on the job here. And he was willing to do his sabbatical here on Islesboro. That's how good the geology is.
Wow.
Which he loves, and he wants to get a house here, and his wife is nagging him to get a house here. We're going to break it. We broke it down into 3 main formations, which are each composed of several members. So there's the formation, and then within the formation are members. And we only chose things that were big enough to be mapped on that could be visible on the map. There were details that were finer than this, but they were too small to be mappable. So the member is the smallest scale at which it's mappable. So each color represents a different member. And so we'll start with, there are 3 main packages. The oldest rocks are what we call the 700-acre island formation. The in-between rocks are called the Islesboro formation. And the youngest rocks are called the Turtlehead Cove formation. I'm going to break it down and walk you through each one of these. So one last thing, one thing that Justin did a lot of, which has been invaluable, is he is really good with radiometric age dating, working out the ages of the rocks using a mineral called zircon. Zircon forms mainly in granite. And so if you get it's very easy to get a good age date on a granite because it's got a lot of zircon in it. The reason they like zircon is they have a lot of uranium in them. And there are isotopes of uranium that are radioactive, and that slowly over time, that uranium will decay to lead. It will become lead over time, at a very predictable rate. The uranium turns into lead. And the way they get an age date out of it is they measure the ratio of uranium to lead. If it's got a lot of lead relative to uranium, it's really old. If it's mainly uranium with only a tiny bit of lead, it's not that old. Does that make sense? Because it slowly converts. It takes about 4 billion years for all the uranium to convert to lead. So that makes it very useful for dating old things, really old things. Now, we don't have any granite on Islesboro. What we do have are a lot of rocks that were sandstones. So when sandstones are, when granites are eroded, that's all the sand and sandstones probably originally came from granite that was eroded, because granite has a lot of quartz in it, and that ends up making the sand. But what also gets included in those are these zircons. And so we call those, I'm going to lose you here, but I'm going to do my best. We call those grains of zircon that have been eroded out of a granite a detrital zircon, meaning it's a grain of sand that is made of zircons. And they're still useful for getting an age date, but the age date is for when the granite formed, not when the sandstone formed. But they're still really useful, and people use them all the time. You see, these are examples of different sands, and they got all those zircons out of them. it's a very time-intensive process to separate the zircons out. But from that, these are all samples from Islesboro. This is the Hutchins Island quartzite, and you notice the youngest zircon they have there is 1.7 billion years old. There are none younger than that. And we've done it in 5 or 6 different places, and we never find one younger than 1.7 billion years old. Which tells us that the rock can't be older than 1.7 billion years old. It has to be younger than that. Now, the Islesboro Formation has lots of zircons that are, this is at 1.8 billion, 1.5 billion, 1.2 billion, all the way down to, we had a few samples that were less than 1 billion. And so that can't be older than, we came with 880 million. The Islesboro can't be older than 880 million years old. But I would say, if the Hutchins Island was being deposited when these zircons were around, it should have them in it. Those younger zircons would be in the Hutchins Island quartzite if they existed at that time. So I think that pushes the age of the Hutchins Island quartzite up to that 1.6, 1.7 billion. I think that's how old those probably are. And similarly, the Turtlehead Cove has a big spike at 630 million, and as young as 514 million. Those would be present in the Islesboro Formation if the Islesboro Formation was younger. So it's probably 600, 700, 800 million years old, the Islesboro Formation. That's how we work all that out. All right. So, this is the 700-acre island formation, which is composed of 2 members. One is the Coombs Marble, named after Coombs Point. This was named more than 100 years ago, where they first recognized this marble. The lime kiln out on Lime Kiln Landing is in the Coombs Marble. That's what they used to make the earliest cement here on the island, was the Coombs Marble. And that's overlaid by the 700-acre island formation, which this is this quartzite that has the 1.7 billion year old zircons in it. So I'll talk about the Coombs Marble first. Here it is on 700-acre island. It's the lavender colored rock. And there it is on Hutchins Island. And actually, we think most of northern Islesboro, the Coombs Marble is the bedrock there. The Coombs Marble is older than the Hutchins Island quartzite. It sits below it. And we don't have any age control on that. So it could be 2 billion years old, 2.5 billion years old, we don't know. What we do know, or what we think anyway, you see how I've labeled these things stromatolites and thrombolites? Stromatolites are produced by cyanobacteria, and they still exist today. It's the first life form on Earth. It's the first evidence of life on Earth, where these stromatolites, which we know today are produced by cyanobacteria. A layer of cyanobacteria will form a mat on the surface. A storm comes in and a bunch of mud is deposited, bound by that cyanobacteria, and a new layer grows, and then another layer of mud comes in, and a new layer grows. And that's what I think produces the laminations in this rock, are these ancient. So this is evidence of ancient life here on Islesboro. They could be 2 billion years old. It's older than 1.6 billion. And then thrombolites are another life form produced by cyanobacteria. And just as an interesting side thing, these are stromatolites from Australia that have been age dated at 3.5 billion years old. So they're the oldest known evidence for life on Earth, are the 3.5 billion year old stromatolites. But gosh, what if these are even older? We don't know. We don't have any good age control. That's what cyanobacteria looked like, if you were wondering. And all life evolved from that. All life as we know it, it started out as this cyanobacteria. We were just at a picnic on Lime Island. I don't know if any of you have ever been out there, but it's just south of Islesboro. But it's entirely it's called Lime Island because it's all composed of the Coombs marble. And look, it looks like a Caribbean getaway. And I think it's all that calcium carbonate from the marble in the water, reacting with the water, that gives it that Caribbean look. And that's overlain by the Hutchins Island quartzite. And that's the rock that we have the 1.6 billion year age on. This is from Gibson. This rock is from Gibson Point on 700-acre island. We also find it on Spruce Island, and it probably formed in an ancient beach in a setting like this, where there were no plants then. So it was a very different looking world then. But there were certainly beaches. And we think it's formed in a beach environment or upper shore face. And yeah, and there's garnet mica schist. This is from 700-acre island, just to the west of the boatyard, on Dark Harbor boatyard. There's a neat outcrop that has all these garnets in it. And they're also an indication of very high-grade metamorphism. So these rocks are the oldest, and they've also seen the most intense metamorphism. They were probably buried to maybe as much as, well, I said 15 to 18 kilometers here, but maybe even more than that, maybe even 25 kilometers. Like they were way down at some point. And then the higher grade schist is present in those rocks. And there it is. One of our big contributions was finding that these rocks are found up on northern Islesboro as well. And that's from Hutchins Island. If you come on the field trip this week, that's where we're gonna go look at these rocks. And there's schist from the same location. And these are images taken with a microscope of little thin sections of the rock, and that's what that mica looks like in thin section. It's very beautiful to look at. And then we recently found it last year on this Shattuck Point, where the big white house is. I guess Lois Childs lives there now. And that, she's got the very old rocks just on that little point of southern Islesboro as well. So, remember the last I showed you of the paleogeographic maps, we were on the west coast of South America, right? Is where we think the rocks of Islesboro formed. So this is now over 1 billion years ago, 1.05 billion years ago, or 1,000 million years ago. And that they have names for all the different plates back in time. North America was called Laurentia, I'm not sure why exactly. And then South America, that northern part of South America where the Amazon is today, the name of that was Amazonia. And I think that is where both the Coombs marble and the Hutchins Island quartzite formed. Was on at that time, the north coast of Amazonia. And that's the approximate location that we now know as the 700-acre island formation. So we're going to go through time. Here, and then there was a collision about 1 billion years ago, and there was another supercontinent. Remember, the most recent one was called Pangaea. That was 200 million years ago. But 1 billion years ago, there was another one that we called Rodinia. And I'm not sure where that came from, but I think that the 700-acre island formation first formed in this setting, and then was part of this plate collision that produced the supercontinent of Rodinia, and that's when that intense metamorphism of those rocks occurred. Now we have some debate on that, but I'm going to keep it a tiny bit less complicated and leave it there. But there it is now 900 million years ago, still buried, 700. Now it's starting to pull apart. Actually, the pulling apart started here. Rodinia, remember I said that eventually the supercontinents rift apart and lakes will form? Well, I think this might be when the Islesboro formation was deposited. It was during the early stages of this rifting. And you see now, So it's spreading apart, and those rift valleys with the volcanism might be occurring. And I think that could be the setting for the Islesboro Formation. And then eventually it completely pulls apart, and you get a little ocean there. So that's the story so far. Now I'm going to get into the Islesboro Formation. And we've broken that into 7 different mappable members. The oldest of which is we call the Barley Ledge, after this ledge out here. It's composed of this, and it's just a quartzite sandstone. And we only really find it on northern Islesboro. I think some of it may extend into Seal Harbor here as well. But we think that laterally correlates with the blue, so it becomes shalier as it goes to the south. That's overlaid and maybe laterally equivalent to this Narrows member, and you see this exposed all around the Narrows area. And it has a lot more shale in it, or what we call phyllite, and that is easily eroded. I was out there yesterday with the Sea Level Committee, and they were asking why the Narrows is so narrow. And there's 2 reasons. One is there are faults that cut through that have weakened the rock there. And the second is there's all this shale in there that's easier to erode than the rocks that are kind of armoring the east coast of southern Islesboro here. So as soon as it broke through that, it was able to quickly erode the center part of the island, because the rocks are more prone to weathering because they're softer. And but that has all different kinds of rocks in it. It's kind of the least attractive of all the rocks. I'm sorry if you live here. But it's sort of it's an amalgam of different kinds of rocks. But actually within the Narrows is one of the coolest formations, which outcrops on our beach, which is a little thin marble unit, we've called the Ames Cove Marble. That arrow is pointing to where our house is right there, and it is really cool. It also outcrops directly under the yacht club. So if you ever hear people banging around on rocks while you're having lunch upstairs at the yacht club, that's what's happening. And it's a beautiful outcrop there. And we were able to trace it all the way down to Pendleton Point, where it occurs there. And that was when we started to figure out southern Islesboro was using this limestone unit, or marble unit, which we were then able to correlate all the way up to the northern end of the island. That was a major piece of the puzzle. Then above that is the Grindle Point member. These are the rocks that are exposed at the ferry dock. If you'd ever walk out, which I'm sure most of you have, and walk along the coast there, that's the Grindle Point member of the Islesboro Formation. And that's characterized by lots of very colorful rocks with a lot of basaltites cutting through them. And that's overlain by the Gull Point member. There's Nancy Alexander and Sue Stafford for scale. They're the ones who got me onto this. And I went, wow, that's because I've been only working on northern Islesboro for them. They were like, you got to come to the southern end. I went down, I was like, yeah, I do have to come down here. And some of the most beautiful outcrops on the whole island are along this east coast of southern Islesboro. Fantastic. The Gull Point is characterized by this brownish, orange-brown color, which is produced by iron-rich, a mineral called iron-rich dolomite. It's the iron in it that gives it that rusty color. And you always know when you're in this because it's completely composed of that color of rock. And it makes beautiful features like this. It's always laminated. It too could have stromatolites in it. I'm leaving that open. We're just not totally sure about that yet. And the way we know it's dolomite is, again, I looked at it with a microscope, and this blue mineral in there is dolomite. But you see all the white dots in there? That's quartz silt. So it's a silty, it's an orange weathering, iron-rich, silty dolomite. And that's what it looks like everywhere. Now, we also find it on the west coast of Islesboro. It's not as thick over here. They're just little remnants on some of the points out here. But that really helped us figure out the big structure of Islesboro, which is something called an anticline. I'll get to that in a minute. But just above that is the Hughes Point member, which darker color that runs down. And we also find it on the west coast as well. It's on Gooseberry Nubble, if you've ever been there. That's Hughes Point member. And then that grades up into something called the Joe's Rock member. It's a terrible name. I didn't choose that one. But there's a transition from the white Hughes Point into this, again, another rusty orange laminated dolomite, silty dolomite, which is the Joe's Rock member. There it is. It's a pretty beautiful rock, though. And again, there it looks almost identical in this section. And from that, because we find the older rocks in the middle and younger rocks on either side, we now know that southern Islesboro is something called an anticline. It's a giant fold. So where we saw little miniature folds up at Turtlehead, the whole of southern Islesboro is a big fold. So it has the older rocks in the middle and the younger rocks on the sides. And that's because it got eroded. Does everybody see how that works from the diagram? How you have your, one would be the oldest rock here, 2, 3, 4, 5. And so that's we think the whole of southern Islesboro is a big anticline, is what it's called.
So did you go in the center of Islesboro
To the extent that we could find outcrop, yeah. We done our, they did a fabulous job. They banged on every rock they could find. And they really did. They did do their best to map it through there. But yeah. And then the Joe's Rock is overlain by a unit called the Dark Harbor member, which I'm going to present a theory on that in a minute. But I actually think the Dark Harbor member, which, go figure, outcrops around Dark Harbor. It's just here, right around the harbor, the Dark Harbor member in here. I think we also find it up on Turtlehead. And maybe on the west coast of 700 Acre as well. And I think it's actually part of the Turtlehead Cove formation. But here we find it sitting directly on Islesboro. And I'll go through that in a minute and what we think there. It's a dark gray rock with little thin white laminations in it. Again, it's a phyllite now. All that Islesboro formation, do you remember the 700 Acre Island formation? We thought had gone through medium grade metamorphism because it has all the schist and garnets and everything. We don't see anything like that in the Islesboro formation, which we think has only seen low-grade metamorphism. So it did not see that intense metamorphism that the older rocks did. So I don't think it got caught up in the formation of rodinia, which is when I think that higher-grade metamorphism occurred. Now, the Islesboro was also cut by all these basalt dikes. And basalt is what's forming in Hawaii and Iceland today. It's an igneous rock. It's actually what forms at the spreading ridges. And when continents are rifting apart, basalt dikes cut up through everything. Because remember, it gets very hot under the continent. And the Islesboro is just riddled with basalt dikes. This is down at Gull Point, with basalt cutting through the Gull Point member. Remember the Gull Point is the orange rock. Just stunning outcrops, really beautiful. Here it is cutting through the Dark Harbor member, these basalt dikes, and they're everywhere. You go to the ferry dock, look for rocks like this that cut across the lighter colored rocks, and you'll see basalt dikes there. So let's pick up the story again. Remember, rodinia was rifting apart, and we thought, and it's in this setting that I think the Islesboro Formation formed. Probably in a rift valley, and I think a lot of those rocks could be freshwater deposits formed in a lake rather than marine deposits formed in an ocean. And I think there are rift lakes all around the world today. The East African rift. Africa has them. There are ancient rift lakes like the Connecticut River Valley, the Newark Basin. They're all the East Coast. The Palisades Sill, if you live in New York City, and you look across the river, you see a big black rock over there. That formed in a rift setting when Pangea was rifting apart. And I think the Islesboro Formation formed in a similar setting, but one supercontinent older, so 600 to 700 million years ago. And then we'll have a look at the Turtlehead Cove Formation, which is our youngest unit. And that is composed of 3 members, the Point Comfort, Cadirs Hill, and Privet members. The Point Comfort member, this is a picture of Point Comfort, is a really beautiful, amazing rock, full of what's a rock called conglomerate. It looks like concrete. It's composed of lots of visible pieces of other rocks, mainly quartz, big pieces of quartz, but we also find pieces of basalt and other rocks in it. These are the thin section from it. This is vein quartz, and that's probably pieces of the Hutchins Island quartzite that have been uplifted and eroded and included in this younger rock. There's an example of it there. You see all the larger pieces of rock in there. And that's a piece of basalt that's caught up in that. So these older rocks are uplifted and eroded, and they're the source for these younger Point Comfort conglomerates. And here it is again down on 700-acre island. It's that brown color there. It's brown here, brown here, brown here, brown out here on Point Comfort. Then that's overlain by what we call the Cadirs Hill member, and that is a green phyllite. If you've ever walked out on the west side of Turtlehead Cove up there, what's called Sprague's Beach, there's neat natural arch up there and caves and really amazing rocks, really beautiful, like spaghetti-looking rocks. And Justin actually found worm burrows in that. That's our first evidence of life since the stromatolites. It looks like, to me, and he thought for sure, that these were produced by worms burrowing around in the sediments. It's the only fossil of any kind we've seen. We never saw a body fossil, only these worm burrows. Also find that Cadirs Hill member, which is the orange on the west side of 700 acre, where it makes these beautiful sort of tombstones standing up. On the Ensign Islands here, they're both composed of the Cadirs Hill. And then that's overlain by the Privet member, which looks a lot to me like the Dark Harbor member. It's black or dark gray with the white laminations in it. So that's the Dark Harbor member, and here's the Privet member. I think they're the same. So it's a fun little thing. So I think this is how it all works out: is that the turtlehead, we changed the names, whoops, but the Privet member is the same as the Dark Harbor member. And above that, it gets much siltier, and then that's what we find all the way out on Turtlehead Point, are these silt stones, or very fine-grained sandstones. And they're all the way at the tip, and they're the youngest rocks, and they're the ones that we have an age date on the detrital zircons of 514 million years. Can't be older than that, it has to be younger. So these are into the Cambrian Ordovician time. When life has exploded at this point, there should be loads of fossils in these rocks. If they were deposited in a marine setting, we don't find anything except those worm burrows. So I think these two might have formed in a lake, in a freshwater setting, and that's why we don't find any fossils of any kind in the rocks, because they should be there if these were marine rocks. And then this was one of my favorite things we found just the past year. This is down the southwest corner of 700-acre Island. We think this is the same as the unit that's on the tip of Turtlehead. But look at the psychedelic folding in that rock. It's just awesome, you know. And so this may be my definitely top 5 favorite outcrops there. And then finally, this is up on here. I'm sorry, I didn't label that properly. Oh, there. Yeah, it's this little unit here. It's our thickest igneous body. It looks like the surface of the moon on this guy's beach, where it's intruding into the green phyllite, the Kadir's Hill. This we think is the youngest unit here, and it's an igneous body. Justin thinks it's fault-bounded. I'm not so sure. I think it might be intruding into it like the neck of a volcano almost, intruding into the Islesboro rocks. So again, I'm going to just take you back to the animation, just to drive this home. Am I going to have to restart it again? Probably. These damn Apple products. I can't even figure out how to close it. There we go. And just take you on this little journey one more time. Now that you know so much more about the geology, here it is. So we're going to go back in time. You remember how this worked. Look at India. Look, want to know why the Himalayas are so high? Watch India. Ready? Boom! Boom! Right? It's fun up here playing God. So we're going back in time. Remember, Islesboro is this little chain. This little chain, it's caught up in this chain of islands, which, for whatever reason, drifted off in the late Cambrian, early Ordovician. See that? It's still part of that Amazonia in the late Cambrian Ordovician. And I think that's when this rift lake might have formed. And then finally it separates from that and takes 100 million years to travel across the ocean and collide with North America. But again, oh, sorry. I'm not doing a very good job of playing God here. So there it is. And there's all the way at the South Pole, where it's sandwiched between Baltica and the west coast of South America. Yeah, because it used to be here. It used to be between that and this, which is crazy, right? But that's what they've worked out. And I have no data to reject that hypothesis, so I like it. It fits what we see here. It explains the basalt dikes, it explains the lack of fossils, even though we're in Cambrian Ordovician age rocks, which should be loaded with corals and brachiopods and mollusks and other things, but we don't find any in those rocks. And so I think a lacustrine setting in a rift valley like this makes sense. Lacustrine means lake, means it formed in the lake. So here we're just going to run through the whole history since then. There's Islesboro coming in. Is one of those part of that chain of islands. There it is colliding with eastern North America. And they think at that time there may have been mountains as high as the Himalayas. And that somewhere deep under that were the rocks of Islesboro getting metamorphosed, and with time they were eroded and brought to the surface. And finally, yeah, just so you understand, and if you didn't get a map, I have 5 or 10 more here, so come get one if you want one. You see all these faults cutting across. I'll zoom in. You see these things? They're all strike-slip faults, meaning they move, rather than one going over the other or down relative to the other, they're moving next to each other. They're sliding along each other like this. The San Andreas fault is a strike-slip fault. And earthquakes are produced every time a fault moves, it makes an earthquake. You got nothing to worry about with these faults because they haven't moved for about 400 million years. And they ain't about to start now. But notice how coves line up on faults. Because the faults fracture the rock up and make it much easier to erode. So the Ames Cove Dark Harbor thing thing is on a big fault. And that's why it was able to erode in and make that so narrow there, is because of the faulting that cuts through there. Pretty much every cove lines up on what was probably a fault zone. And then finally, a big part of the story here on Islesboro was the glaciation, the ice ages that came much, much, much later. In fact, this is a map from only 18,000 years ago. Now that we're talking billions, right? This is just a drop in the bucket 18,000 years ago, but there was more than a mile of ice above us at that time. And that scraped the whole island clean. It was just barren rock and maybe some piles of till and outwash and things after that. I don't have time to go through all that, but that's going to be the topic for next year's talk, is the glacial history of Islesboro, which actually plays a major role today because a lot of people have built their houses on glacial clay. Well, they didn't build them, but they are built on glacial clay, which the recent storms have unfortunately really been eroding at an alarming rate. So understanding that whole history and where these glacial clays are on the island, I think, is another interesting topic to follow up with. So that's it. I want to thank all the landowners who so kindly allowed us to walk on their beaches, whether they knew it or not. Thanks to all my colleagues. I mean, all praise goes to them, and to Patrick and Amanda and the Historical Society. Thank you.
Anyways,
Oh, that's good.
two questions if there are. Yes.
I just want to comment that the storms that we had last January moved a lot of stuff around, covered a lot of things up.
Yeah, crazy. I know, I was out on Hutchins, and like 15 feet of the island was eroded. I mean, it's amazing.
Yeah,
Yeah, you see trees that were up on the bank 15 feet from the current bank.
so maybe a lot of the discoveries, but I'm afraid something might be covered up.
It actually made the outcomes much better.
Did it?
Yeah, well, it made our work even better.
Oh,
Yeah,
great.
because it uncovered a lot of new outcrop that was once under the soil, under the clay. Yeah, but not that we want that, but we saw some interesting things. Yeah, we have time. Yeah. Oh yeah.
So if Islesboro collided with Africa once,
Yeah.
are some of the rocks here from Africa?
That's a great question. Well, some people have even, you know how I said that I think they mainly formed on what's now the west coast of South America. Other people have proposed that some of them formed on Africa. And I don't know enough to refute that. But that's a great question for future research, yeah. And definitely, like Florida came from Africa. I don't know if you noticed that in the animation, but the whole southeastern U.S. was part of Africa before, and it got sutured on to North America when it drifted apart. Yeah.
Can you play why fossils don't form in freshwater?
Well, they do now, but maybe they haven't evolved yet to live in freshwater. I'm not sure. Yeah, but there definitely are gastropods, snails that live in lakes now.
So the date of these rock formations, there's no we've never found a fossil that formed in those.
Well, I didn't research it for too long, but I the oldest lacustrine fossils, and they were like 200 million years old or something. I'm not don't quote me on that. Yeah.
So where my mother's property comes down on the northeast side of Privet into Parker Cove,
Yeah.
and with the January storms, her whole bank is made of clay. And there's
Yeah.
like 8 feet of trees that have all come down.
Yeah.
Are you saying that the glaciers are responsible for making all that stuff clay, or is it the fault?
Well, if you come to the Hutchins Island, this leads me into the Hutchins Island field trip, where you're going to see beautiful glacial features there, including the clay. There's two kinds of soft rocks, soft sediment that came from the glacier, at least two. One is till, which is bulldozed up while the glacier is advancing, and one is the clay that formed when the ice melted. It was full of, you think of ice as being white and pure, but a lot of times it's full of clay and rock, chunks of rock and things that it's picked up, and you have a mile of that. And as it melted, all that clay settled down onto the seafloor and made a layer that probably covered everything at one time. And over time, that's just getting slowly eroded away, you know, in the last thousands of years. And so the clay actually, it feels like clay. It feels like we could make a pot out of it. Sometimes it's blue. It's really very beautiful. And there's like little tiny rocks floating in it. But then if you see giant pieces of rock floating in it, then that's probably that earlier till that was bulldozed up by the glacier as it advanced. So, but we'll have to go have a look. I think I know what property you're talking about. Parker Cove is between
It's between Hutchins and,
Point Comfort.
yes,
Yeah.
yeah,
We'll have to go out and have a look. We can look at it when we go there.
yeah.
You'll be the expert after the field trip. So there's this hurricane, another hurricane coming, Hurricane Debbie,
Yeah.
which I think is going to rain us out on Saturday, it sounds like.
Yeah.
So we were talking about, the IIT has a bird walk that they scheduled right at the same time as our field trip. And then they had already chose a rain date. They were quick with the rain date, which is Sunday. So we might do the geology walk Monday morning at 9. If any of you are free to attend that. We'd meet at Hutchins and walk out there.
Will you post it if it is special canceled, or are you just saying you're
It's-
going to push it to Monday?
No, it's canceled on Saturday.
Yeah, I think,
Rescheduled for Monday.
That's why I got.
Yes.
yeah, I'll put it on Facebook, yeah.
Okay.
And then you had a question.
Because of the different ages of rock, does that mean the rocks here have been subducted multiple times? Kind of
Well,
down
so,
and then
yeah.
up and then new rock down again?
I kind of blew over that part, but it was when no I didn't. It was when we collided with North America that the low-grade metamorphism happened, the phyllite level. It was when Rodinia formed that very old rocks saw that higher grade of metamorphism. Do you remember, like 1 billion years ago? That's my theory on that. Stay tuned. It could change, subject to change. But yeah, so it's just been so fun to work on this. And from this, I have like 2 or 3 new projects in mind, the things that I'm going to follow up. I'm going to be a little sad not to have new beaches to wander, because they did too good of a job making the map. And, but some neat new projects to work on. Yeah, you had a question?
Oh, yeah, so, I saw in your Facebook post that you said we could bring some rocks, and you keep talking about there's no fossils, and I have been looking for fossils in this island for 17 years, and I always find the same fossil, and so I brought the fossil that we have
Yeah, I know exactly what it's going to be. But it wasn't from bedrock, it was from a floating, rounded
I
rock.
don't know, we have a bunch of these, I don't know,
Yeah, it's probably from western Maine, with brachiopods in it. Is that what it is?
It looks like a
Let me
little
see.
shell.
Let me see.
Oh,
Because
lights,
people-
I mean lights.
People find these all the time. Yeah. I never found one, so I may have to take this.
I got a bunch of those.
Yeah. But I think that is a brachiopod. Yeah. Good job. Good eye. Oh yeah, definitely. Definitely. So this is from western Maine. How did it get here?
In a truck.
How did it get here from western Maine?
This is not the only one.
You found it
From the ice picked it up and brought it.
This comes from we live on the hills from Portuguesa, we're very south on the west coast. And I found several of these on the same kind of rock and the same exact shape, all of it.
So as the ice advanced, it picks up bits of every rock that it runs over. So we have chunks of granite from Canada here, the rocks that have traveled thousands of miles probably. For the rock idea, just come up to me after. Anybody else have a question? Well, thank you so much.